All right, let's continue. Any questions or comments? Now I want to give some examples to Berry phase. I have two examples. One is an example we know about, so let me start with that quickly, and then I will spend more time on the main example. So this is Aharonov bone phase as Aharonov bone phase as Berry phase. So the setting is like something like this. Suppose I have like a particle in a box, like something like that, and the corner of this box is like something like this. Like let's say this is R, and I want to put like a solenoid here, like that. And I want to imagine taking this box and slowly rotating, okay, maybe like the lower edge. So without changing the orientation of the box, I want to take this lower edge and slowly rotate around this flux tube and bring it back to its original place. So this is the setting. So this edge of R in this case is R is three-dimensional vector. So this is R1, R2, R3, X, Y, Z. It's going to be 1 over 2m P plus E over C A squared plus V of R minus R, right? So R is so the corner of the box is R, and corner of the location of the electron is, so this is R, and this little distance is R minus R. So this is the box potential we trap the electron in, and electron we are imagining can never go out of the box, and the flux is completely constrained inside the tube, so there should be no classical magnetic field affecting the influencing the electron. So, and we now know how to deal with this thing if psi n of R minus R is a normalized eigenvector with epsilon of n, then so this is with A is equal to 0. In the presence of A, we just put this vector potential, so-called chiral space, minus I E over H bar C. So this is going from R to R, the R prime A of R prime psi n of R minus R. And I want to call this, again, a short name. Let me call it theta. And I want to calculate Berry phase and Berry connection and Berry curvature, all those things. So NR in this case is this wave function, n of R, I del R, n of R is equal to I. Now we need to integrate over all possible positions. So this is e to the I theta psi star n R minus R. So this is del R e to the minus I theta psi n of R minus R. So that's the integral we need to take. So this thing is going to either act on theta or this, and if it acts on theta, it's going to pick up an A factor. If it acts on this, it's going to go through theta. So let me write that. So this will be e to the minus I theta minus I del R theta plus del R psi n of R minus R, right? So that's something like that. And this, if you take the derivative, this is going to be, right, derivative again, the same thing, derivative of integral e over h bar c times a of, you can see this is a derivative with respect to r, and I think there may be an overall minus sign because r is in the lower side, but let's not worry about that at the moment. If you want, there's minus I plus, but there may be overall minus, and this one is del r. So I will just rewrite this whole thing. So this a of r is going to go out. So this is because it's not integral variable. So this is I e over h bar c. So d cube r, and these guys again did their job, and we can cancel them. So this is psi n star of r minus r, psi n r minus r, plus, and the second piece, I, let me write it in the second line, it's not going to fit. So d cube r, psi n star of r minus r, so this is del r psi n of r minus r, right? Oh yes, here, right? Yeah. I forgot to write that. Yes, thank you. So this is a of r. So first, so this thing, what is that? We are working with normalized wave functions, so this is 1. And similarly, so this thing, so if you take the derivative of this thing with respect to r, there will be two terms, one acting on here, one acting on there, but one will be related to the other, and you can see, maybe I can ask you to think about this, because it's also a trivial calculation, it's going to be 0. Then our Berry phase, in that case, I think I forgot, so there's one I here, another I here, so this is going to be plus. And because the R is in the lower limit, right, so this is in the lower limit, not in the upper limit, so there must be an overall minus sign. So then what we are saying here is the Berry connection, A, this double A, n of r is going to be minus e over h bar c a of r. So Berry connection is basically vector potential in that example. Up to this e over h bar c, and there's also minus because electron charge is negative. So Berry phase gamma n, just integrate dr dot en of r. So it's going to be minus e over h bar c, and we know this line integral of vector potential, you can use Stokes theorem to relate it to flux, total flux, and this thing is going to be equal to 2 pi flux in units of flux quantum. Then this says Berry phase is Aharonov-Bohm phase. Berry connection is vector potential, and Berry curvature B is going to be, right, because of this we can think about Stokes theorem and relate it to magnetic field inside, and it's going to be related to magnetic field. Good. So that's nice, that's how it should be. Now I want to, okay, we have a good time to think about the main problem. Let's think about the most quantum thing in nature, which is spin a half. So spin a half in B field.
How is this different than the Aharonov-Bohm?
It is exactly the same thing. Right? That's a nice thing. Like the initial Aharonov-Bohm effect we got it from like some complicated, right, path integral, and then we said there is like a Peierls substitution, and then you integrate it. Here it is like two-line calculation. Once you understand the geometry of quantum mechanics, it just comes out for free.
Yes, I understood it, but the new topic, I mean, in one and a half.
Oh yeah, this one is going to be quite non-trivial, yes.
Okay.
So this one is the structure will be similar, but interpretation will be very different. For example, we will have to think about magnetic monopoles in that case. That's why it's very non-trivial, but let's just take one step at a time. So the setting is like we have some external magnetic field, something like that. So this is B field, and in this B field we put a half spin. So this is S, and the question is what is the Hamiltonian of this system? So H. I think everybody knows that, but let me see. If you don't know, it's okay. What is the Hamiltonian of a spin in a magnetic field? B dot S. So B dot S, but if you do the scaling, I want to write it like this. So S is what? S is H bar over 2 sigma, and sigma are Pauli matrices, sigma X 0, 1, 1, sigma Y 0, minus I, 0, and sigma Z 1, 0, 0, minus 1. So I want to absorb this inside everything I don't want. That's why I want to write it like this, H dot sigma, and H is equal to Hx, Hy, Hz is 3D parameter space. So we had R in the derivation of Berry phase. Now we are going to think about Hx, Hy, and Hz. But
are you generalizing the coordinate system? Like using these, we are not constraining ourselves to any coordinate system, right?
we are not. Yes, we are not. But like any Hamiltonian, like if you have H of R, R's are like, it looks like coordinates, but it wasn't, right? We said it is like a position. Of course, it is here in the Aharonov-Bohm example. It is the position, but it doesn't have to be. It can be any parameter in the Hamiltonian. As long as you have the ability to slowly change that parameter and come back to where you started, you can play this game. And in that case, H is going to play the role of R. So the 3D vector is like something like that. So we have, so this is H vector. There are like two angles. One is azimuthal angle, and the other one is maybe this is polar, this is azimuthal, right? This is X, Y, and Z. And here I will do this calculation in terms of this polar, spherical polar coordinates, but you could also do it Hx, Hy, and Hz. So let me write it H like so. So there's like some magnitude times, let me just write it, sine theta, cosine phi, sine theta, sine phi, right? Sine theta, sine phi is going to be y, and last component is going to be just cosine theta. Then H dot sigma is going to be H. So this is cosine theta. This is minus cosine theta, right? This is the Z component. And here I have sine theta e to the minus I phi, because there's sine theta, one comes with cosine theta times minus I times sine theta, and this is from earlier formula, this is e to the minus I phi, and this side is going to be sine theta e to the I phi. Good? So now we need to find eigenvalues and eigenvectors of this 2 by 2 Hamiltonian. Of course, you can put it in Mathematica and it's going to give you something, but it's very easy. Let me try to do it real quick. So there are two eigenvalues, right? And the trace of H, which is, right, in terms of eigenvalues, is going to be lambda 1 plus lambda 2. And the trace here is 0, so it's going to be 0. And the second one is determinant of H, right? Any determinant is product of eigenvalues. And in this case, it's going to be H squared minus cosine squared theta. And if you multiply this, minus sine squared theta, right? Because e to the i's just go away. And this is going to be minus H squared, right? Then lambda 1 is equal to minus lambda 2, and their product is minus H squared. Then I'll choose the exact minus H. Lambda 2 is H. So we found the eigenvalues. But we also need to find eigenvectors. Eigenvectors. So this thing, let me just copy. So this thing, I want to focus on lambda is equal to minus H, this smaller eigenvalue. Let me write it like A and B is equal to minus H times A and B. So cancel H. From here, from the first row, like cosine theta A plus sine theta e to the minus I phi B is equal to minus A. So combine these A's. 1 plus cosine theta A is equal to minus sine theta e to the minus I phi B. So this is cosine square theta over 2 plus sine square theta over 2. This one is cosine square theta over 2 minus sine square theta over 2. This one is 2 times sine theta over 2 cosine theta over 2. And there will be a lot of cancellations. So this sine square is going to cancel this. So this is going to be 2 cosine square theta over 2 A is equal to minus 2 sine theta over 2 cosine theta over 2 e to the minus I phi B. So this one is going to cancel this one. Okay, let me just write in 2 lines. So this one is gone. These 2 are gone. So this one is gone. And so we want to have normalized eigenvectors, and from here I can see what it should be. So if you choose A is equal to, actually let's choose A positive, it doesn't matter, but it's like let's choose sine theta over 2 e to the minus I phi, and if we choose B equal to minus cosine theta over 2, so these are the eigenvectors, then A, B is going to be sine theta over 2 e to the minus I phi minus cosine theta over 2. And I will call this the negative eigenvector. Good. Now, here parameter space was hx and hy, but h is fixed. Now the new parameter space is theta and phi parameter space. And we need to calculate Berry connection, Berry curvature, and all those things. First, let's start with Berry connection. So this, let me not write double A, it's kind of awkward. Now we know it is Berry, but if you want to make sure, you can be a little bit more careful. So this is A minus of theta is equal to I minus del theta minus. And this thing is this. And if I take, okay, there's like minus I, I. Let me just push it just a little bit. So this is I. Dagger of this, or maybe I can just write transpose and make this plus. And the other one is going to be just derivative of, with respect to this is going to be derivative of sine is cosine theta over 2 times 1/2 e to the minus I phi, and derivative of minus cosine is sine theta over 2 1/2. Hopefully what I write here is clear, right? I'll multiply this with this plus this with this. So it's going to be I 1/2. There is like these complex exponentials will cancel. It's going to be sine theta over 2 cosine theta over 2 minus cosine theta over 2 sine theta over 2. So this is product of this and that, and it's 0. And a phi minus is exactly the same thing, but derivative like this, and this piece is going to be the same, but this piece is going to be cosine theta over 2 e to the minus I phi. That's it, right? Or maybe minus I, and this one is 0. But I'm taking derivative with respect to phi. There is no phi there, right? Oh yes, it is. Yes, it is sine. Yes, you're right. This is sine theta. Yes, sine theta over 2 e to the minus I phi minus I. Yes, thank you. And if you take the product, so this minus I is going to cancel this I. So this is going to be sine squared theta over 2. Let me check that. Yes, that's correct. Now, okay, we calculate Berry connection, Berry curvature. This omega mu nu becomes theta and phi because there are two indices. That's the only thing we need to calculate, and it's going to be equal to del theta a minus phi minus del phi a minus theta. Right? I just rewrite the same equation but in terms of theta and phi. And this thing is already 0, so there's nothing to calculate here, and I need to just take the derivative of this thing is going to be 2 times sine theta over 2 cosine theta over 2 times 1/2, and cancel that, and it is going to be, I want to write it 1/2 sine theta. Good. And let's calculate total Berry curvature, which is integral of this thing over all possible theta and phi's. And this one is going to give you 2 pi. These two cancel this, so this is going to be pi, and theta goes from 0 to pi. It's going to give you what, 2, right? And the result is 2 pi. And we can also think about a sphere. You don't have to integrate over all things, right? So we can think about like a path on this. So the magnitude of h is fixed, and suppose the vector h, you just circle around this blue and come back to where you started. In that case, this gamma minus is also very easy to calculate. This is going to be dr dot a minus, and it is going to be this area, this S dot omega theta and phi minus, and we calculated omega theta minus. This is just that, and so this is equal to 1/2, because there is 1/2 sine theta, the phi, the theta sine theta, and this is exactly 1/2. Let me call this C contour, the solid angle subtended by this contour, right? Whatever that angle is, you know that it is the value, and that's the Berry phase. So this is the Berry phase. Now I want to, like, from this result, right? This result says the total, if you integrate over all Berry curvatures, you get 2 pi. Then we can also think about Berry curvature as a function of given orientation, right? And let me write that and ask you to think about it just for a minute. If, for example, in the Coulomb case, we have, let me first write that, right? Gauss law. We have Gauss law, and it says that if you integrate over all A times E, it's like Q enclosed, maybe divide by epsilon 0. And if you have like a point charge from here, you know what is E. So this is like a vector, 1 over r squared. And since it is like a vector, it is better to write it like this, right? It is r over r cube. There is like overall factor, but we don't mind. And the same thing here. You integrate over all angles, and you get 2 pi. Then it's reasonable to conclude. What notation? I used B here. I didn't use double. So this B is going to be 1/2 h vector, exactly like r. We now have h vector divided by h cube. Okay.
So that's what we call monopole.
Exactly, and that's the interpretation. Like this is like a magnetic monopole in parameter space. And the gap between lambda, okay, I will ask you to do this. You can run all of these calculations for plus, right? First, you need to find, okay, we already found the positive eigen value. You need to find eigenvector corresponding to this positive eigenvalue. And you run these calculations. And you are going to find it is like going to be minus 2 pi. And what this means is like lambda plus minus lambda minus. The gap between these two states is going to be 2h. And monopole sits at origin of parameter space at degeneracy h is equal to 0. So when h is equal to 0, these two states are degenerate, and we cannot define Berry phase there, right? For us to be able to define Berry phase and Berry conic, all these things, we required a gap from the beginning. If you don't have gap, you don't have adiabaticity, and all these things, they do not work. And that point where the gap closes is the degeneracy is the monopole. Yeah, that's the interpretation. So let me give you one more exercise, and I want to make a little bit connection with some more important topics. But let me just give you homework. Like use this formula we write omega mu nu n, which is equal to I think in the first hour I said there's like an alternative form. So this n prime is not equal to n del mu h and n prime del mu h n prime n, and divided by En minus En prime squared. Use this formula and Hx, Hy, Hz Cartesian components to find exactly the same thing, to find the same results and verify this monopole at origin. B is equal to 1/2 h over h cube monopole. So there, if you follow this calculation, you can find each Hx, Hy, and Hz components, and it can like tell you about the value of this this formula. So let me start with topological. So this is topological or geometrical magnetic monopole. Later, I will also connect to Dirac monopole. And the picture is something like this. We have like sphere in this parameter space. So here, suppose I have some path. It's not very important. There is some orientation. Suppose I choose this orientation, and there's like inside. So this is the inside. And I want to, I also want to generalize this to spin S. Generalized. Okay, here's also one more homework if you want. Homework. Generalize this calculation to spin S rather than spin a half, and what you are going to find, for example, is like this. B is going to be S times H over H cube. But now I will use it. It's not very essential to derive it. Generalized to S. And here, Bayer phase from this path, gamma, is some S times, so let me call this curve C, solid angle subtended by this curve C. So that's the Bayer phase, right? We found this here, right? In that case, there's like a contour, and the Bayer phase is solid angle taken by this contour times a half. In the spin case, we replace 1/2 with S. However, there is a problem, right? In the sphere, what is inside of curve and what is outside of curve is not clear, right? It is an ambiguous thing. I could just copy exactly the same figure, and I can just say outside is my inside, and I can change the orientation. So this is like this, and outside is my inside. Nobody would know this, right? How do you define one is inside? You are on the think about equator, right? Am I going to take the top of the sphere or bottom of the sphere as inside? So this one is gamma bar, and this is going to be exactly the same thing, the spin S times the curve C bar. But Bayer phase is a phase, right? Bayer phase is a phase. So gamma is a phase, which means it is defined mod 2 pi. That's the meaning of the phase, because phase comes with e to the I something, and if e to the I something is shifted by 2 pi, you wouldn't know the difference. Then this gamma should be equal to this gamma bar modulo 2 pi. We require this because nobody would know the difference. But we know, so this solid angle taken by C plus solid angle taken by C bar is equal to what?
4 pi
exactly 4 pi. Yes, just yeah. And from here we know omega of c bar is equal to 4 pi minus omega of c. Also here, because I reversed the direction, it has to be a minus sign, right? Because we reversed the orientation, there's like overall minus sign because of the orientational change. So this formula I want to use, so I want to multiply it with minus s, and okay, this is going to be a little bit cluttered equation, so this is minus s, okay, so this is plus s, minus is plus s, so this minus s times, so this minus s times gamma c is my gamma bar is equal to minus s times 4 pi, so this one is my gamma, and that automatically means gamma bar, or okay, let me write it the other way, not write this gamma, minus gamma bar is equal to 4 pi times s, or it is equal to 0 mod 2 pi, right? This is equal to 0 mod 2 pi only if s is equal to 1/2, 1, 3/2, 2, 5/2, and dot. So what this is saying that is like spin has to come in multiples of 1/2 for us to be able to have this phase in a meaningful way, right? So this basically explains spin is quantized in units of 1/2. Okay, so this is exactly the Dirac quantization, but generalized to this geometrical interpretation. Because we have time, I want to also go through the Dirac quantization. So let's think about that, and it is not related to any of these things. Like even if you have like just a little bit quantum mechanics and a little bit electrodynamics, you can derive this thing, which is I think one of the most important things Dirac did. So let's consider Dirac monopole and see the similarities. Actually. So we know we cannot write magnetic monopole, right? It's not possible. But suppose we could. Suppose there is. We know experimentally it's not possible, but suppose there is like magnetic monopole. If there was a magnetic monopole, it would be something like B was equal to exactly what I wrote there. Some strength G, or if you want, this is like magnetic charge times E of R divided by R squared. Exactly like Coulomb, right? But it is generalized to the magnetic charge. Now use magnetic Gauss's law. And this is going to be like ds dot B, which is going to be equal to, right? There is like R square d cosine theta d phi, and this thing is going to come with G times 1 over R square. This one is going to cancel this, and at the end what you are going to find is 4 pi times G. So that's the magnetic charge. However, magnetic field is not like electric field, and the reason magnetic field is not like that is like we require B to be a curl of some vector potential A. Right? That's like a difference from the electric field, and that means if I have like a sphere, right? Like if I enclose some region with like a sphere, And if I take a very tiny curve here, like suppose I'm just taking a very, very tiny curve in the North Pole, I can just use, so this is C if you want, ds, this is the area vector here, S dot B. I can use Stokes theorem, let me write it like dl dot A, and it's going to be enclosed flux, phi enclosed, right? But we know as you shrink this curve to 0, the area will go to 0, right? And there's nothing you can do. Phi will also go to 0 if no singularity. And this will be important just in a little bit. But we said we can also consider what is inside and what is outside is, right, ambiguous. We can also consider exactly the same thing, but rather than that, okay, the curve is the same curve, but I changed the orientation in the other direction and I just consider outside, right? Because we cannot, I mean, nobody can tell me to do that. I can choose outside as my inside. In that case, this dl dot A is going to be equal to, right, as C goes to 0, I'm going to pick up all the phase, all possible phase, and because of change of orientation, there will be minus 4 pi times G, which is phi enclosed. But we initially found flux to be 0, but now we are saying flux is not 0, flux is 4 pi G.
But again, inside the contour and outside the contour, there must be similarities, right?
Exactly. Now we are coming to here. If these two results are not giving me exactly the same results, I come to the conclusion there has to be a singularity punching through the sphere at some point. It has to be, like, there must be some singularity coming inside the sphere. Otherwise, right, I cannot reconcile. If the surface of sphere is smooth for every point, this one and this one has to be the same. But as you can see, as I take this loop and go up to cover entire sphere, something is changing. Then that loop has to pass through a singularity. This calculation is telling us, at least screaming us, that look, there is like a singularity, 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 right? So this means
Is the second result phi enclosed or minus phi?
So I say like enclosed flux, right? So this is the definition of phi enclosed. In the second orientation, there's like a minus because of orientation. The enclosed flux is negative in the second one. In the first one, it is 0. Now we have like there must be singularity. And Dirac said, okay, the singularity is coming something like that. So Dirac's argument is like, so here there is like so-called Dirac string. So some very infinitesimal tiny flux tube enters the sphere from the top, and it just emanates this required flux from everywhere. So this is the Dirac string singularity. Good. So that's what Dirac said. I'm almost done. But where does the string enter, right? It can enter from here, it can enter from here, and it can enter from there, right? And Dirac said different entry points correspond to different gate choices. Okay? So different entry points are related by gauge. So you can, by making like a gauge transformation, you can take this string and put it like that, for example. And he said, then a like curve, like this blue curve, the Aharonov-Bohm phase picked up by this blue curve should be undetectable. If you can detect something like gauge dependent like this, you are in trouble, right? He said the Aharonov-Bohm phase in this blue curve C should be undetectable, and this one is going to give us E over H bar C. This is our beloved Aharonov-Bohm formula, is exactly the same thing. So this is dl around this little curve dot A, and this is equal to what? This is equal to 2 pi flux divided by this H bar C is going to give me 2 pi, like I just erase it like, and 2, and it's going to be phi naught. And phi we found is equal to minus, but let's forget about minus, 4 pi g. And 4 pi g so this thing is okay. I'm just now writing this is 2 pi 4 pi g over hc over e, right? So this is hc over e. I got this one 4 pi. Okay, I see. So I cancel this one and this one. I put 4 pi g. So this is going to be equal to m, where m should be an integer. Good.
If there is a magnetic monopole,
Mm-hmm.
then the divergence of magnetic field is not zero anymore.
Yes.
How can we define a magnetic vector potential then?
Exactly. You cannot. That's the key. So you cannot define a unique vector potential. In the electric field, you don't have a problem because you don't have the curl of electric field. Here you do. What you require is like you need to define at least 2 vector potentials. One is never enough. So one is going to work everywhere except South Pole, and the other is going to work everywhere except North Pole, and these 2 vector potentials should be consistent with each other. If you want, there is like some more story about that. But at the moment, so our conclusion is this, right? You can actually do all of these arguments by defining these 2 vector potentials, and you can require these 2 vector potentials to be to be consistent. But here, let's see what this gave us. By the way, so this is Gaussian units. In the SI units, this C will go because that's typically what people use. Let me just write it. So this electron charge times magnetic charge should be equal to, there is like 1/2. So H bar is over 2 pi times m. And exactly like spin quantization, from here we see that even if we have just one in the entire universe, one magnetic charge, that explains E is quantized. So initially we quantized the spin in units of 1/2. Now we are quantizing the charge in units of magnetic charge. And that's the reason people believe there is like a magnetic monopole, right? At least many theorists believe it has to be somewhere. It has to, and we just cannot see it, but they hope that we'll see it one day. Okay, I think that's it. Any questions, comments? All right, thank you.